First, I just want to start the second half of our program by thanking the audience. So you've been wonderful so far, asking great questions, and it's always a sign of a good event when you can't get people back in to sit down because they're too busy talking to each other. But so now we do get to hear a couple more presentations, and then we'll have this panel discussion, and then we'll have even more amazing snacks at the end where you can continue the conversations that you began. And I should just tell you that, again, please think up questions that you want to ask each individual speaker, but then keep in mind the ones that you didn't get to ask or that apply to more than one speaker for our joint discussion at the end. And so again, before I continue, I'll just explain that these two talks by Ben Schneiderman, who's our special guest from the University of Maryland next week, the first one will be a very large venue in Science Center D, but you're still requested to register if you want to come. And that one is about algorithmic accountability. So the reason I mention this now is because you heard the question to Nathan at the end, which I'm sure will come up again in the discussion, essentially about what do we do about the fact that we have these algorithms that either we don't know what they're doing or they're being applied for sometimes less than completely honorable reasons, not by Nathan or Legendary Entertainment. But we can talk about Mr. Zuckerberg later. Anyway, speaking of Harvard alums, or almost Harvard alums, I lied to you when I said that the next speaker wouldn't be a Harvard alum. She does not have a Harvard PhD like the previous two speakers, but she does have, I believe, an undergraduate degree from Harvard University. Renee, do you have any Harvard degrees? Okay, unless we suddenly confer an honorary degree on Renee, we're gonna be good. You want an honorary degree? Okay, wait about 30 years and then we'll give you one. Okay, so anyway, but her master's degree is not from Harvard, it's from Johns Hopkins. This is Saki Takahashi, who I'm talking about, in epidemiology, and her undergraduate degree was in applied math. And currently, she's a graduate student at Princeton University, which I hear is a pretty good school. It's okay. Anyway, and we learned about her work from our colleagues in epidemiology here, and also from the leader of her lab, whose name is Jess Metcalf, who some of you might remember as a speaker in the wonderful Contagion event that my co-director of science here, Janet Rich-Edwards, organized back in the fall. And what Jess was talking about was essentially the use of data on difficult problems in epidemiology, but in this era of the availability of lots of large online data sets. And one aspect of that that particularly interests me, that I'm really eager to hear about today from Saki, is looking at spatial distributions and temporal distributions and bringing the tools of other fields of science and other fields of statistics to epidemiology in ways that either they weren't there before or were not possible before. And I'm being purposely vague because she's going to show you now what that means as soon as I put the microphone back together. So let's welcome Saki, and I can't wait to hear what she says.
Great. Thank you so much. Thanks to the organizers of this event for inviting me here. So today I'm going to tell you about some of the work that we've been doing on combining different data sources to generate fine-scale maps of susceptibility to vaccine-preventable infectious diseases. And this work is really exciting to me because it was driven by real-time public health policy questions. And it's especially exciting to be here because I actually first got involved in epidemiology and public health as an undergrad. I had a mentor in the biostats department at the School of Public Health who introduced me to people in the epidemiology department. And needless to say, I got hooked, and I've been doing infectious disease epidemiology since then. So I know that you guys have hosted previous events on epidemiology, so perhaps you've come across this map before. For those of you who haven't, this is a map of cholera cases in London that was made by John Snow in 1854. And he traced the source of the large cholera outbreak, and cases are shown as these black rectangles, to the famous Broad Street pump, shown in red. John Snow is known as one of the founders of the field of epidemiology. But I'm going to argue that he was also a founder of spatial epidemiology, and my talk will be on spatial epidemiology. So one infectious disease that I and a lot of people in my field think about often is measles, which, as you may know, is one of the most transmissible and potentially deadly infectious diseases. it has a high R naught, or basic reproductive number, of 10 to 20. And R naught is the expected number of secondary cases caused by one infectious individual in a completely susceptible population. And so basically, R naught is a metric of how transmissible an infection is. And so let's compare that to the R naught of, let's say, seasonal influenza, which is around 2. The R naught for measles of 10 to 20 is quite high. And measles is a leading cause of death in children under 5 years of age, and measles still kills almost 90,000 people each year. And so here's a toy schematic to give you an idea of how transmissible an infection with an R naught of 10 really is. So individuals who are susceptible to a disease here are shown in green, and infected and infectious individuals, or the infected and infectious individual, is shown in orange. And now let's say we have a completely susceptible population, so everyone's green, and then we introduce a single person who has infection with a disease with an R naught of 10. On average, that one infected person will cause 10 new infections. So in addition to R naught, a key concept in infectious disease epidemiology is herd immunity. And herd immunity is an indirect protection against an infectious disease that occurs when a sufficient proportion of the population is immune, or in other words, vaccinated. And herd immunity is related to R naught in quite a simple way, which is that from epidemiological theory, we know that the proportion of the population that must be vaccinated in order to actually achieve herd immunity, or what we call P of C, is calculated as 1 minus 1 over R naught. And so this means, from a programmatic standpoint, the higher the R naught is, the greater the proportion of the population that needs to be vaccinated. And so for measles, which I said earlier has an R naught of 10 to 20, this means that roughly 90 to 95% of the population actually needs to be vaccinated in order to eliminate the disease. So now, here's that same schematic again, showing a measles-like infection with an R naught of 10, except this time we vaccinate 91% of the population. So there are 11 people in our population, and 10 out of 11 are vaccinated. Vaccinated individuals are shown in blue, and let's assume that vaccine is perfectly immunizing. And again, we introduce a single infected person into that population. This time, the infected person won't cause any new infections because a sufficient proportion of the population is vaccinated, and so they won't get infected. In addition, the one person shown in green here, who wasn't vaccinated, will also not get infected because they're protected by this concept of herd immunity that I introduced earlier. So measles vaccination is one of the most cost-effective public health interventions, and this is because measles, the disease, has both a potentially high case fatality ratio of up to 20% in some situations, as well as a safe, effective, and inexpensive vaccine. And so this figure here is showing the number of reported global measles cases in blue bars from 1980 to 2016, and the corresponding yearly vaccination coverage during this time period in blue and red dots. And you can see that the gains in vaccination coverage that have been made over recent decades have led to a large reduction in measles vaccine cases globally. And so as a result of this, all WHO regions and countries currently target elimination of measles, the disease, by the year 2020. However, continued measles virus circulation in many countries makes this goal seem particularly elusive. And as I said earlier, measles is still one of the leading killers of children globally. And so to get a more clear picture of what vaccination coverage estimates in that previous slide that I showed actually represent, this is a map showing reported measles vaccination coverage in 2016 by country. And you can see that across countries, there's quite a bit of spatial heterogeneity in coverage. And countries where coverage is particularly low, which is so below the 80% threshold, is shown in light and dark red. So there's quite a bit of spatial heterogeneity. And countries in sub-Saharan Africa have some of the lowest vaccination coverage levels. And this is also where the majority of the world's remaining measles cases are found. So what I'd like to try to convince you in my talk is that it's important to think at an even more local level. And since a country level estimate, so any of these single polygons, is still an average, a country can have high overall coverage, but also have pockets of low coverage, and that could sustain a measles outbreak. So now I'm going to tell you a little bit about how measles vaccination is actually delivered with a focus on sub-Saharan African countries. So there's two ways in which measles vaccine is delivered. First, by routine immunization at health centers, and this targets young children at 9 months of age for their first dose of measles-containing vaccine, which we call MCV1. Secondly, countries conduct catch-up campaigns, and they're known as supplementary immunization activities, or SIAs. And the purpose of an SIA campaign is to boost population-level immunity. And they do that by targeting a wider age range of children compared to routine immunization. So SIAs will sometimes target kids up to 5 years of age, but even possibly older, even up to 15 years of age in some scenarios. And so what SIAs, or these catch-up campaigns, do is they both provide a first dose of vaccine to kids who were missed by routine immunization, but they also provide a second dose to those who were already vaccinated by routine programs. And in many countries, we have kids getting 2 doses of measles vaccine. And these campaigns can be conducted across an entire country, or they can target a specific geographic area, and they're conducted every 2 to 5 years. So this equation for P of C that I mentioned earlier, which represents the proportion of the population that needs to be vaccinated, this equation assumes that susceptible individuals are evenly distributed throughout the population. And so this doesn't account for any heterogeneity across space. And in reality, the spatial clustering of unvaccinated people, and unvaccinated people being susceptible people, right, makes it even more difficult to actually achieve herd immunity. And let's compare that to the situation where the same number of people are randomly distributed across space. And so along those same lines, estimating vaccination coverage by taking the average across large spatial areas could miss zones of vulnerability that are small, or those that don't follow administrative or political boundaries. And this has been increasingly recognized among public health policymakers and is reflected by a shift from simply setting country-level targets to a focus on ensuring uniformly high vaccination levels across a country. And so in 2010, the World Health Assembly set a goal to achieve 90% measles vaccination by country, as well as at least 80% coverage in every district within a country. And so in response to this shifting focus towards more detailed geographic information and equity, we've been setting up an analytical pipeline that combines data with models that incorporate the 2 mechanisms of vaccine delivery towards the goal of understanding measles vaccination coverage at the subnational level. So the primary data that we use are demographic and health surveys, or DHS. These are large cross-sectional, geolocated, and nationally representative household surveys. They're a rich and publicly available source of information on demographic and health indicators, including vaccination, and they're conducted across over 90 countries. And they're usually done every few years in each country, and they ask hundreds of questions using a standardized framework. And so every survey has information on thousands of participants. In particular, a DHS survey has information on each interviewed woman's child who are 5 years of age or younger at the time of the survey, and it includes relevant dates, their date of birth, their date of survey, and from that we can calculate children's age. And then there's also information on their measles vaccination status, which we're really interested in. For some children, we have information on their date of vaccination from their vaccine cards, but for others, we only know that they were vaccinated based on their mother's recall. Lastly, we have data on their GPS locations at the level of household cluster. And what cluster here means is it's an aggregate of households, and there are 300 or more of these clusters per survey. So on the right here is the data from the DHS survey that was conducted in Madagascar in 2008-2009, and that's the most recently available survey from that country. And there were over 10,000 children included in this survey, and each point on this map corresponds to a GPS cluster. And the color of the point reflects the proportion of children who are vaccinated against measles, and then the size of the point corresponds to the total number of children in that cluster. And so the information that goes into the DHS vaccination data comes from individual vaccine cards, such as this one. And you can see here, for this child, you can see their date of birth and their date of measles vaccination. And if you do the math, they got their measles vaccination at around 9 months of age, which is the recommended age. at least in these contexts. And this is what the country-level vaccination data in that Madagascar DHS survey actually looks like. And so this histogram is showing children's age at receiving measles vaccination, if we know it, and that's in months. And this is information that comes from vaccine cards, like the one that I just showed you. And you can see that for a majority of children for whom we know when they were vaccinated, they got it at around 9 months, but there is a distribution around that. And this histogram is a different way to look at the data, which is children's measles vaccination dates that we got from the DHS survey, also from the Madagascar survey. And this is binned into month and year of vaccination. And the months with the turquoise or pink bar contained a measles vaccination campaign. And in Madagascar, they actually do 2 campaigns a year to try to catch up kids. And so you can see that months associated with a campaign have higher vaccination dates on cards. So this kind of is a signature that these campaigns are doing something. And so for each child in the DHS survey, what we do is we take information on their vaccination status, their age at the survey, and then their age at the vaccination, if we know it, and then we fit it all into a likelihood-based model, and then we estimate parameters that describe the probability of any child being vaccinated given their location. And so we've been developing these statistical methods that we think are widely applicable to countries that have DHS surveys. And so as we were working on these methods, the West African Ebola epidemic was underway. And so in addition to the considerable morbidity and mortality as a direct effect of Ebola, the epidemic also disrupted the normal means by which routine healthcare was delivered in these countries. And this is because Ebola shut down the health infrastructure in the affected countries. And so disruptions in routine healthcare lead to a reduction in vaccination rates, and that leads to a reduction in increasing population level susceptibility to measles, especially in the young age cohorts. And that can lead to a breakdown of herd immunity. And so Guinea, Sierra Leone, and Liberia had all been concerned about growing measles susceptibility in their countries and had planned to conduct these catch-up campaigns in the future. And so our program manager at the Gates Foundation told us that given these shutdowns of health services due to Ebola, measles outbreaks are inevitable. And it would be good to have some sort of risk map to show and to guide a preemptive response. And so for us, this was an opportunity to apply the methods that we've been developing to analyze the geolocated DHS vaccination data. And what we did was we pulled the most recently available DHS survey from affected countries and surrounding countries, and we pulled information on their most recent SIA campaigns that they've done. And our aim here was to map and quantify how Ebola-related healthcare disruptions increase the risk of a measles outbreak, and that could create a potential second public health crisis following Ebola. And so we've observed that measles epidemics frequently follow humanitarian disasters. For instance, a survey of households that were displaced due to the Ethiopian famine in 2000 found measles to be a contributing cause in 35 deaths. Measles epidemics also follow disruptions in the health system due to natural disasters. And the current political conflict in Syria has also led to large numbers of measles cases due to the collapse of the health system. So now I'm going to take you through the steps of our analysis pipeline and how we applied it to understand how Ebola-related healthcare disruptions increase the risk of measles. So first, we obtained the geolocated DHS vaccination data that I've been describing from these countries at the epicenter of the Ebola outbreak as well as the adjacent countries. And then we estimated the relevant vaccination parameters from our model at the DHS cluster locations, and we incorporated the 2 mechanisms of vaccination, both routine healthcare services and these campaigns. Inevitably, we don't have DHS data from every single point in space, which is what we would like. But what we do is we take our estimated parameter values at the locations for which we do have data, and then we interpolate, or we assign their values to locations that are unsampled, and we assume that neighboring locations should have similar parameter values. And so this, you might have heard of, is essentially the first law of geography, which is that everything is related to everything else, but near things are more related than far things. And so this map is showing the baseline probability of receiving routine vaccination by 2 years of age, and these are at 5 kilometer by 5 kilometer grid cells. And so we see that there's low vaccination coverage in Guinea and Liberia overall compared to Sierra Leone, but there's considerable within-country heterogeneity in vaccination coverage as well. So we use the DHS data to estimate the baseline or pre-Ebola vaccination estimates, and then we applied this framework to look at the effects of a reduction in vaccination due to Ebola. So reports during the Ebola outbreak were indicating that at least half of healthcare centers were closed and that those that remained open were receiving fewer patients. And so what we did was we looked at the effect of a 75% reduction in routine vaccination rates, and this was based on the best available information we had at the time. And so we used those reduced vaccination rates to estimate post-Ebola vaccination coverage. And so what we did was we took our DHS survey estimates, and then we combined them with data from the World Pop Project. And they have high-resolution, age-structured population size and birth rate information. And those are based on satellite data on human settlements. And so on these maps, lighter colors indicate higher population density. And so now that we have this additional demographic data, we take our proportions of vaccinated children, which is from there, at each location, and then we can generate the expected number of unvaccinated kids at a given age. So the last step was to project the population forward in time using the spatial birth rate data and under different scenarios in which routine vaccination is disrupted for 6 to 18 months. And so what we did was we mapped and then we counted up the number of children who were unvaccinated against measles under 5 years of age in the region, under this assumption of a 75% reduction in vaccination rates. And then what we found was that with every month of healthcare disruption, an additional 19,000 children are unvaccinated against measles in the 3 focal countries. And so you can see on this map here that susceptible children reside in these contiguous clusters that cross national borders. So to summarize this work, we know that the Ebola outbreak led to a significant disruption in healthcare services and a corresponding reduction in routine childhood vaccinations, including those against measles. And then based on our synthesis of DHS survey data with high-resolution demographic information, there would be these large connected clusters of unvaccinated children. Some of the caveats of this work are that the exact numbers of susceptibles depends on the values of the reduction in vaccination, and that could vary spatially based on factors like local Ebola incidents. But regardless of the exact numbers, there's a clear path to avoiding outbreaks of childhood vaccine-preventable disease, which would be to conduct a multi-country vaccination campaign aimed at age groups that were unprotected. And a robust campaign could virtually eliminate the risk of measles in the region. So we've heard secondhand that this analysis, which we published during the last year of the Ebola epidemic, was useful in motivating a public health response. So in Liberia, there was an outbreak of measles in the first half of 2015, and a follow-up national campaign, vaccination campaign against measles as well as polio was conducted that June. And so we've worked with various organizations to do specific follow-up analyses. And then in the Lola prefecture of Guinea, which is near the Liberian border, there was also an outbreak of post-Ebola measles in the first half of 2015, and there were over 700 suspected measles cases. And this was another example of Ebola-associated disruption to the healthcare system, since an SIA campaign had been planned in Guinea during the previous year, but it was interrupted by the Ebola outbreak, and it actually never got to Lola prefecture. And so Matt Graham, who was a postdoc at Johns Hopkins at the time, led some of our work in estimating susceptibility to measles in Lola and forecasting the course of the measles epidemic. And this was done with the European CDC and the WHO. And so to conclude, measles vaccination is a best buy in public health. The DHS survey data are an invaluable resource for understanding the spatial distribution of health indicators, including childhood vaccination. And I hope I've demonstrated that this type of work that leverages various data sources and applies spatial analysis techniques can reveal useful insights for real-time public health planning and advocacy. So with that, I'd like to thank my mentors, my collaborators, and funding sources, and thank you very much.
Thank you very much. Okay, so we'll take just a few questions now for Saki, and then some more afterwards. Oh, the microphone, you sound good.
So I was really interested in the demographic data that you used from the satellite images. How does one link just population density to population density of children, or are you just making a correlation that there's some average number of kids per number of people?
Yeah, so these are actually age-structured data. So they go in and estimate at 5-year intervals, like the number of 0 to 5-year-olds, 5 to 10-year-olds, 10 to 15-year-olds by pixel.
You can tell the number of 5-year-olds from space?
Apparently.
Wow.
Yeah. Well, so it's based on like demographic projections by like UNDP and whatnot, and like fertility rates and those things like go into the estimation. But yeah, it's amazing. Yeah, it's pretty cool.
I had a clarification question on the R0. I'm kind of assuming that in the background there's some assumption about kind of how many people the typical child interacts with. That's in the background there somewhere. And I'm wondering if you could also tell us a little bit about the state of the art in regard to, say, the social graph structure, in the sense that, you know, there may be some super connectors who interact with a lot more people, and kind of what does your literature have to say about that problem, and how should we be thinking about it?
Yeah, so for your first point about R naught, so that's something that for the context of measles, transmission is driven by kids in schools usually. So there's some great work showing that like during the schools, like when school is in session, measles R naught is higher. And then when during the summer term or winter vacation, R naught goes down, and that's because kids aren't mixing in schools. And so there's a whole like literature around the seasonality of measles. And then in terms of, I guess, mixing and so I think that what this work does is like it sets the baseline level of susceptibility, but then when you're actually thinking about transmission and like epidemic dynamics, it gets much more complex, because you have these nonlinearities, right, between susceptibles and infecteds, and you know it's so I guess all I would say is that like trying to understand susceptibility is possibly a more tractable question. I think that, so in other work, I also think about like epidemic dynamics and how like transmission plays out in the population. And I think you have to think much more about like how kids contact or how people contact each other, like, you know, that not just by space, but also by age. So there are these studies that show that essentially mixing patterns between age, like there's this diagonal where like I'm more likely to interact with people of my age, but then there's also these interesting like off-diagonal effects where parents and children interact, right? And so you, like there are some strong mixing patterns between those age cohorts as well. So yeah, it's a really...
I'm going to take the microphone to ask a follow-up question, which will be the last question, which is just, so I'm very interested in spatial epidemiology, and part of the problem is that these R naught models, the very basic models, just assume, you know, who's infected, who are they going to transmit it, and have no spatial information whatsoever. And so what you've done is take smaller and smaller spatial cells and then model those, you know, very carefully, and then get a spatial map of what's going on. And there's interactions within those spatial cells of different kinds of people to, you know, answer David's question about transmission. But is there in your modeling any interaction between the cells themselves, and does like that spatial relationship of the individual dots?
Right now it's completely static, but I think that this could probably serve as the basis for dynamic modeling. Right. Absolutely, But there's not, we don't have kids moving or interacting in these flat maps.
Yeah, we'll just get slightly better computers and slightly better data, which is the answer to all questions in this session. But anyway, thank you again.
Thanks.
So now we will move to the largest scale of today. We will move to the entire universe. And I will read a sentence which is actually true, which is that Renée Hložek's goal is to understand the structure and amount of dark energy in the universe, constraining theoretical cosmological models with observations. So for those of you who don't study astronomy, that means that she's actually studying the fundamental mysteries of the universe. And we don't understand like 95% of the universe, optimistically. And part of what Renée does and the kind of data science that she's going to talk to you about today is something that people in astronomy have come to appreciate in the last decade or so, what used to happen in astronomy is that people would make observations and then they would try to back out what the physical parameters that explain those observations are. Now there's a lot of what in statistics often would be called forward modeling, where you say, okay, I think maybe I understand the physics. If I make a prediction, to go back to Nathan's world, about what the universe would look like under those assumptions, what would that look like? And that's what Renée will probably call a model, or a cosmological model in her case, of the universe. And then the statistically difficult stuff is to get enough data and enough clever statistics to constrain the difference between the models and the observations. And sometimes people even go so far, and I don't know whether that's what she'll talk about today, but to make synthetic observations, to take these models and then make fake observations as if you have real telescopes. And so part of what distinguishes Renée's work is that she's actually interested in those real telescopes, even though she's trained as a theorist. So I should explain that she did not go to Harvard, but we let her come today anyway. So Renée is originally from South Africa, and she went both to the University of Pretoria and the University of Cape Town. And then she went to Oxford, where she got her DPhil in 2011. And I met Renée sometime around then, I don't know, at a funky sci-fi event at Google, and before that once. But Renée has a lot of extracurricular interests, not unlike Nathan, and she was, among other things, a senior TED fellow while she was all these other things, including she was a postdoc before her current assistant professorship at the University of Toronto, where she's also at the Dunlap Institute, which I should mention, but she was a postdoc at Princeton of many flavors that involve the name Lyman Spitzer, who's one of my great heroes in astrophysics, and you can ask me why later. That's not important right now. What's important is that Renée is going to tell us about the most modern techniques in trying to understand the mysteries of the universe. So no big deal.
Thank you so much for having me. It's wonderful to be here. I'd like to state for the record that I had my measles and mumps booster a couple of months ago. I'm definitely going to see Pacific Rim Uprising, and I promise to stop adding extra noise to your tweets because I often post that I'm really glad to be alive and I really like the universe and space. So I'm going to stop that now and only be mildly pleased by the universe. But I do have the best job, and I'm probably going to tweet about that later. So thank you so much. So I used to live in New York City for a year while I was at Princeton, and one of the reasons why I like bringing that up when I talk about what I do is because while Hurricane Sandy gave us many terrible things, one thing it did give us was darkness. And so I'm going to take you back to Sandy. So this photo was taken by Jared Levy through a darkened lower Manhattan. And imagine that you were here. You can see there are cars on the road, but there are no street lights. And you want to cross the road and not die. So what do? You typically, if you've grown up in a city, you look at the cars approaching you, and if their headlamps are bright, you realize they're probably close to you and will kill you if you cross the road, and so you don't. And if their headlamps are faint, you realize they're probably far away and you cross the road. But did you ever ask who told you to do that? Like, who taught you to do that? If anyone has grown up in a city, you just learn how to do that because you understand that there's a connection with brightness and distance. But it relies on a fundamental assumption. It relies on the assumption that the person who put the headlamps in the car put them in with the same brightness. Otherwise, that whole calculus you did in your head without thinking would fail and you'd cross the road and die. So we call these things standard headlamps, or if you're in cosmology and you like to be a little bit archaic, you call them standard candles because that sounds cooler and candles were a thing back in the day. But we do this in astronomy too. We actually use exploding stars that we think explode with roughly the same brightness wherever they are in the universe to tell us something about the distance. So for example, this is an image of the Whirlpool galaxy, and I'm going to tell you there's an arrow there which is going to guide your eye. But even without the arrow, if I show you an image taken before and after, you'll see that there's something there that wasn't there before. And this is an exploding star, exactly similar to the kind that Nathan was talking about, an exploding supernova that shines very brightly in its galaxy. And so these objects actually allow us to make a measurement of distance in the universe. And I care about that as a cosmologist because if I understand how big the universe is, that tells me something about what the universe contains and also how it changes with time and how it evolves and all of these really grandiose questions that I want to answer. In order to measure these kinds of objects, I need to build bigger and bigger telescopes. And so this is the wonderfully named Large Synoptic Survey Telescope, or LSST, or as I like to call it, the Careful What You Wish For telescope, and I'll tell you why in a second. This is being constructed in northern Chile. I have a great movie of the construction later, as Alyssa said, but I didn't put it in the beginning of the talk because I figured it was too dramatic. But we can get to the dramatic parts in a bit. And LSST is really incredible because it has incredibly amazing instruments, and it looks at a large part of the sky at any given time. So it has a 3.5 degree diameter in the size of what it looks at, so that's 7 times the diameter of the full moon in the sky. And if you were to point the Hubble telescope, which we all know and love, to take images of that same patch, you need 3,000 images of Hubble to patch that whole sky. So it's really incredible. And the way that you do this, the way you get a telescope like this, is you build a giant camera. So this is a 3.2 megapixel camera. So and it's about the size of the gentleman who has no head is to scale. So the LSST camera is about the size of a Volkswagen Beetle, which again is a car from the past. But the incredible thing is that LSST will scan the sky very rapidly. So it'll scan the whole sky about once every 3 days, which is something that really isn't possible now with current telescopes to that same depth and to that same precision. And that allows us to really see the sky in a whole new light. So if we take a journey back in time to pre-2000s, if you digitize old plates from telescopes, you get something like this. You can see the sky, and it's really incredible. And I'm going to show you what it looked like post that. So this is coming out a little dark, but the Sloan Digital Sky Survey was a small telescope that also scanned the sky a lot and really revolutionized astronomy when it came about in the 2000s, because until then it hadn't been possible to really scan the whole sky. And so one of my old advisors as an undergrad said that Sloan essentially did his entire body's work of 20 years in about 3 weeks. So it really revolutionized things. But LSST, this is a simulation of what LSST will see. It will just be incredibly deep and show us really incredibly large numbers of objects that we just haven't seen before. So the projected estimates are that we measure something like 40 billion stars and galaxies. Those numbers start to sound astronomical, or for want of a better word. And what it'll actually do is now we can start to see the sky not only as static, but really as transient. That there are objects that come in and out, as Nathan introduced us to earlier, these objects that brighten and then fade. And if you looked at the sky, this is a simulation of the kinds of objects or the kinds of explosions that we would expect to see with LSST. You expect to see so many of these supernovae of different kinds going off in the sky at any time, which is great. So we're going to get vast amounts of data from LSST. But you have to be careful for what you wish for. Mm-hmm. So I like analogies because I'm a professor of astronomy, and we have so many cool things we can make analogies to. And so I like to say, imagine if all the supernovae that we know of up to now, that we are really study very well with smaller telescopes, let's just assume those are all modeled by a fish. This fish, I can see it very well. I understand it's got some cool lip action going on. There's fins. I can look at its markings, and I can understand it very well. And that's fantastically useful if I want to understand this one fish. LSST is going to give us something more like this. I'm going to get a lot of data, but now I can't really tell how many types of data there are, how many different kinds of fish there are. Actually, this comes from a study on coral diversity, and it's really hard to find images of schools of fish that are not just one type of fish. But apparently there are 148 different species of fish in this image, according to the website that I shamelessly stole it from. And it's both a fantastic challenge and it's incredibly scary, because now we really need to know about each different type. The reason why that's important is the kinds of stars that I use to do cosmology with, that really are intrinsically bright everywhere in the universe, those are a very specific subset of these supernovae transients. They're called type 1a supernovae, and they have this relationship. But other dying stars, similar to the ones that Nathan studies, they die when they are at the end of their lives, and they die with different various masses. And so we don't have the same correlation with explosion and distance that you would have. And so if I just use all of these fish, assuming they're of one type, I'll actually get a very different answer than if I hand pick out the ones that I want. But I can't hand pick out so many fish because I need them to look like this. And I know they will look like this. So the question is, well, how do we classify astronomical transients? I'm going to highlight some of the work by myself, but also lots of my colleagues who are really exploding in interest in this field, and it's really fantastic. So again, this was introduced before, but we do something typically called indifference image. I take a photo of you today, I take a photo of you tomorrow, I remove the average, which is just how old you are, how tired you are, and then I probably see that you were crying this afternoon or something like that. Probably don't cry at the end of my talk, but we do this in space, and so we take a photo of a galaxy today and tomorrow, and if we see a difference, we know that an explosion has gone off, and you see this, what looks like just a boring white dot is actually incredible because it's showing us that there's a transient at that position in the galaxy. This allows us to build, because we have different filters on LSST, so we actually measure the sky not just in optical light, but we select very specific wavelengths of light, and so we can actually measure what does this transient look like in different filters, and we give them very original names like R, G, I, and Z, and Y. And so you can see the brightness of the object in these filters change as a function of time. And the way that they change with time is luckily different for Nathan's supernovae and my supernovae. Sorry, I'm throwing you under the bus now. You did it to Alyssa. So one of the ways you can distinguish these different types of supernovae or type of transients in general is to fit some kind of, to extract some features. So I know that there's a light curve. Can I describe it in some way? Can I figure out what the components of the light curve are? Or can I fit a template to it? And myself and other colleagues do a lot of these kinds of approaches where you find out the number of features that describe this light curve, and then you can train your machine learning classifier on that using various techniques. And these are great, but it helps. The key in this area is really to understand the clustering of these objects. So what types of supernovae or what types of transients have the same characteristics or features, and how do they cluster together, which is really important. And so some of my colleagues spend a lot of time making graphs like this. So this is a t-distributed stochastic neighborhood embedding. And the only thing you need to take away from this plot is if the areas are overlapping in this space, you can't tell them apart very well. What you want is actually in this particular dimensional representation, you want all the little types or classifications to be separate. And one of the things we find in astronomical supernova data is that actually we have a lot of overlap. A lot of the things look a little bit like each other. If I change the characteristics of the supernova explosion, it could look a little like a variable star, which is again very interesting, but not telling me about cosmology necessarily. And so one way that you can do that is to try and reintroduce some sort of balancing to your data. One of the things that happens is some kinds of objects are much more probable to occur than other kinds of objects. And so when you look at a set of data that you get from a telescope, you get a whole lot of one kind and none of the other. If I want to then train some classifying algorithm on that training data, it's going to do very well at classifying this kind of data and very badly at classifying this kind of data. Just like if you've never met a South African, it's hard to classify my accent. But the more South Africans you meet, the better you get. And so the way that you can do that is either bring more South Africans into the room or kind of copy me. So make different copies of my accent, change it subtly to try and make the balance in the room a little bit better. And this is what some of my colleagues do. Another thing that's really interesting is to try and say, well, can I, rather than removing features, can I turn a light curve into an image and then apply a lot of very interesting visual deep learning techniques? So this is, again, from a colleague of mine who has done this and is now able to, instead of saying, I think I know what features are in this light curve, turn it into an image and apply something like a convolutional neural network to try and do this classification. And it's shown that they do pretty well. This is a little side note because I asked a colleague of mine at Toronto about the work he's doing in machine learning, and he told me about craters on the moon, and I just had to share it with you. It's not related to astronomy of exploding stars, but I thought it was really cool. We see craters on the moon. Turns out they're very hard to find and identify. Did you know? I did not know that until a couple of days ago. And so a colleague of mine at the University of Toronto, there's a lot of data and there are a lot of craters, and typically grad students go and circle them. They see what if they have them. But the little craters are very numerous, and particularly the backside of the moon doesn't have a lot of images taken of it. And so these colleagues at Toronto actually developed, again, a convolutional neural network to build up templates of what they think the circles of the moon are. And then there's some data that you can use to validate your result. And they can identify 92% of the craters that exist in images, and they're having a great time at the back of the moon. So this is really cool work that I just wanted to highlight. But that's a little diversion. One question that we ask is, can we actually skip this difference imaging completely? So the problem with taking an image of me today and an image of me tomorrow and taking the difference is sometimes something will happen to the image that introduces an artifact that's not real. So, I could, if I'm not wearing exactly the same outfit, something moves, you might think that there's a transient, but actually it's just a factor of the image processing. And that happens a lot, particularly with things like cosmic rays. So these are things that come not from a cosmological origin, but just more local to the instrument, and that can really influence your result. But some colleagues of mine have said, well, listen, we can model a galaxy plus a little star, and we can train our neural networks to predict that and then test it with data. And actually they're finding pretty great results where they don't need to just take differences between day 1 and day 2, which is really useful. So how do we get ready for LSST? So something that I've become very involved with recently is trying to do better at simulating what we think LSST will be like. People talk about turning the faucet on and data just comes streaming out. And the big problem with LSST is that even though we can write down what we think the data rate will be, we've just never seen this many objects because we've never had a telescope that is good enough to look with such precision and such accuracy and such repeated cadence. So it is going to just be a data deluge, and you have to try and prepare yourself for that. So as I said before, we have a problem that often the data that you train on isn't representative of the data that you receive. And we know that that will be the case with LSST because it's just looking deeper than anything has before. So what we can try to do is actually simulate data sets and collect all the data to try and make something more representative. So this is just another example of that, where the training data in black were used on the testing data, and you can just see that those two data sets are really not representative of each other, and so you really struggle, your algorithms really struggle to predict the rate if all you had was the black to train on. And so some of the work that a colleague of mine, Rafael, is doing in the audience is actually collecting data from lots of different surveys within a particular area of the sky that's been well studied, and also trying to say, well, so these on the y-axis is different types of variables, and trying to figure out, can we oversample where we need to? Can we build complete light curves? Can we actually build a good data set that people can use to classify on with existing data? And this partly inspired us to do this from a simulation standpoint as well. So with Rafael and others, I'm actually leading a group of people around the astronomical community who are bringing their theoretical models. So they're actually bringing the models that they've inferred from data. And now we're saying, can we simulate the sky? Can I tell you, I'm going to make a sky that has supernovae and type 1a supernovae and core collapse supernovae and transients and variable stars and asteroids, and throw them all together, and then open it up to the machine learning community and in general, not just astronomers, to say, we're going to give you an object of about, a data set of about 1 million objects as a function of time. Can you classify them, and how well are you going to do? And what happens if we change the cadence of how often LSST looks at the sky? So this is really exciting work, and it's proving to be very interesting and very complex as we try and piece apart the ways to make the data rich and usable, and also to engage people that are not just astronomers to try and help us understand the incredible sky. I'm really lucky that I'm able to do this as my job, but looking up at the sky shouldn't just be something, I think, that is reserved for people who live in universities, because trying to understand what goes bang in the night is something that matters to all of us. Thanks.
We'll show the other beautiful movie at the end of the discussion. But anyway, we can take questions now. Go ahead.
Nice talk. I have kind of a niggledy-piggledy question on the stochastic clustering embedding chart. What's the rationale for not including individual points?
One of the things, I mean, you can try and do a clustering over multiple axes. So in this sense, well, you mean just the visual representation, why we used a KDE to smooth it out? I think that's basically just to make things look a little bit better as the plot. So one of my bugbears for everyone who's interested in data science, typically the plots that we make are really ugly because they're like plots in a TSNE plot showing some kind of clustering, but if you look at it, it's not really sure what you're supposed to believe, or a rock curve that literally just looks like every other rock curve. Sorry if anyone uses them a lot. So using the KDE was a way, I think, for particularly for my colleague, Gautam Narayan, to actually make it a little bit more tactile and show some sort of 3D-ness, even though that's not necessarily real, rather than just individual points. But the points are there, they're not sort of hidden or anything.
One more question for Renée, and then we'll bring everybody back together. So go ahead.
Simple question. When the James Webb eventually gets launched, when the James Webb telescope eventually gets launched in 2 or 3 years, something like that, is that going to, I mean, that's looking at longer wavelengths. Is it going to produce a lot of new information on these kind of events that you're talking about?
So one of the interesting things about longer wavelengths is that, of course, these objects, supernovae, behave differently. Different kinds of supernovae behave differently as a function of wavelength. And so one of the cool things about some supernovae is they have another bump. They rise again in brightness in the infrared, which is very useful and very interesting. James Webb will go very deep and will be able to give us incredible resolution. So this will definitely supplement us. But in the supernova community, because we're really looking, wide areas of the sky, it's actually one of our biggest problems is finding other surveys that can really match the area that we're going to survey. And as far as I know, James Webb will not do a significantly better job at actually overlapping with us, although we're going to bring all the data that we can to overlap.
But there is an interesting point in our community in general that there is this emphasis on both very targeted, very narrow observations like James Webb can do, and then these huge surveys. And so there's a lot of times people think data science is about huge data sets and just only hugeness of it, but there's also this kind of how do you optimally combine different kinds of data, which I think goes across all of our fields here. So why don't we sit down and talk about that? But anyway, thank you again. So we're going to do this for about 15 minutes. We'll have everybody come sit in the front here, and then we'll have our little party. Although this is like here. So I have a couple questions to get us started, which we'll start with the one that I just almost asked. But then please, we'll just go to the audience because I can ask them questions later. You don't have to hear that conversation if you don't want to. But this question that I just asked about this challenge of combining a lot of different diverse data sets and a lot of different sizes of data sets and types of data. And then I think that there's this kind of public perception that the macho data science or the good data science is just about the gigantic, enormous data sets. And so you don't all have to answer, but if anybody has thoughts on that particular, the perception both within the data science community and in the broader public where they don't understand that diversity of data, different kinds of data is so important.
I mean, one of the things we're doing with LSST is actually figuring out, we know that LSST only takes images, so it can't take a very fine spectrum of energy as a function of wavelength of the objects. And there's some benefits to taking a kind of spectrum like that where you learn a lot of the very fine physics of the explosions. And so we're trying to figure out, what surveys can give that to us and how to design that. But I think one of the things that is a real challenge is if we throw a huge bunch of data, kind of to the point of inference versus prediction that Nathan brought up, if we just throw a bunch of data at a machine learning algorithm that we don't really understand and we get an answer that is predictive but doesn't tell us about the physics, I'm much less interested in that because that just means I found a cool new object that I don't understand. But I really want to know, is there something weird in the explosion mechanism or is the dark energy changing with space or time? And so we need to do much more targeted small surveys as well as the big ones, I think.
I think so.
One of the ways that we think about this at Legendary and the way that we've actually structured our group, our analytics division here in Boston, and I think you see this more and more in sort of data-oriented groups in industry is that we actually have a separation in the teams and the types of people we hire for between the data science skill set that I sort of spoke about and represented here today and the software development and data engineering skill set and perspective. And it's really useful for us to have that specialization because it means people with an interest like mine who are really interested in developing models and understanding and modeling systems can focus on that, and we can benefit from the incredible skill set that our colleagues on the software development side, data engineering side have to be able to assemble and wrangle and help us to combine together those different
I'm
large
really
data
glad
sets.
that you brought up this specialization because my most pressing question is David still here? Yeah, David Parks, who's one of the co-directors of the new Data Science Institute at Harvard. David wave so people will know and they can talk to you afterwards. David was present at a conversation where I won't name the other people involved because it's important not to, but the conversation was about science and the future of science and whether or not knowing anything about actual science, like principles in science, matters, or whether you could have this version of science that was put forward on the cover of Wired magazine a decade ago where people were like, the end of theory. There was a big X on the cover of the magazine. And the idea was that if you have enough statistics and enough data that you can just infer everything and that you don't have to understand things like, I don't know, gravity. And so you can tell from my tone of voice that I don't really subscribe to this point of view. But on the other hand, you noticed in Nathan's talk, and I want to ask the other speakers too, but in Nathan's talk, you were talking about things that had very human terminology, do they like robots, or do they go to the movies after dinner or before dinner, and these human concepts of dinner and robots and all that. Or for those of you who don't know very much about data science, a lot of it is about feature vectors, and so some of like what Renée was just showing in these t-SNE plots are very abstract. They're not a physical property of something. They're something that shows up again, repeatedly statistically, and not even the experts know what they are. And so there's this tension between like human interpretable things that you can measure, like what you were talking about, Nathan, and then not. And I'm just curious what in your various fields you think about. I mean, you talked about humans in the loop, but I'm talking about something slightly different, which is like human interpretable features, shall we call them. So.
Yeah, I think there really is a sort of division in the data science community between people who do have a scientific background and are interested in learning from data, interested in making...
That's maybe the inference part, yeah.
Exactly, right. Interested in inference, interested in being able to learn from the comparisons between models and data to update our own theories and our cognitive model for how a system works. And people who just are coming from a different background. And as I sort of alluded to, I think the model that we have at our company, and I think a model that's really successful in general, is to have both those skill sets represented and to allow the interaction between them, to literally have those individuals collaborate to get to the best possible outcome.
Yeah, because there are these sort of warring factions. But I'll turn into a more specific question for Jen. So you were talking about manipulation in China, right? But a lot of us, most of us, I think, live in the United States, and we wonder about those kinds of things in the United States. Facebook manipulating our lives, things like their emotional contagion experiments and all of that. And so if you think about that, some of the data scientists at places like Facebook, which I'm sure comes to mind, especially given where you live very often, do and don't care about the kind of whether they understand what the algorithms are telling them and what that means about real people rather than just what it tells them about improving the algorithm. And so what's your opinion? Like if you were going to apply what you were doing and you were going to try to have a sort of social, emotional, psychological, whatever, but in a kind of human language way, what would you do that would change anything about what you're doing? And what do you think that has to do with what's going on in the US? That's like 5 questions in one.
That's a lot of questions.
Pick any of them.
And actually, so picking up on this point, I think from a social science perspective, there's a lot of pushback against data science, computational social science, machine learning because of the focus on prediction versus the focus on inference. So as social scientists, we want to do inference. We don't want to do prediction.
Which is the human understanding
exactly.
side. Right.
But computer scientists and others, engineers are coming in and doing prediction on these human behaviors.
Right.
And there's now, so how can those communities, instead of being at odds with each other, kind of collaborate together.
Exactly.
And I think where it happens, at least in the areas I'm in, is in causal inference. So as we want to know what causes certain types of behavior on individual societal levels. So are there ways of using more of these predictive tools to do more individual level causal inference?
Yeah, and I'm also curious, I'll ask one last question, I'll turn it over to the audience, but just for Saki, I had the pleasure at one point of meeting Ban Ki-moon during the Ebola epidemic. And I was interested then in spatial epidemiology too, and he told me that the reason that apparently the predictions about the epidemic and the spread of the epidemic were mostly too pessimistic. At least that's what he told me. And he said that the reason was because the models of human behavior and how well they would cooperate with health officials and with instructives were wrong, and that people were more cooperative than they should be. And so how much of that kind of human factor stuff comes into what you do, and how good are we at modeling that?
Yeah, so I guess in terms of just simple epidemiological mechanistic models, we don't usually incorporate the human behavior element. But there are social scientists and people that we work with who incorporate, rational behaviors into the epidemic process. So basically, if you see a lot of other people who are infected, you're more likely to, stay away from them or like quarantine yourself or So there are, and that's it's called a rational epidemic, and that's something that, I'm very interested in, just because there's a bunch of cool new data coming out from social media, people using Twitter data to look at how behaviors spread on a network, right? And so specifically in my field, it's vaccine refusal or human behaviors about health. They also spread on a network, just like diseases spread on a network. So there are a lot
Good
of
to hear.
links to the social sciences, I think.
Okay, great. Now I will fulfill my promise. Go ahead.
I actually also have a question a little bit about the interpretability and probably mostly about the inference domain. But so with the explosion in data science, there's obviously a lot more budding data scientists. I think then there are people willing to undergo this strong quantitative type of training, let's say a PhD in statistics or a related field, right? So I was wondering if you guys had any idea maybe for how to, mitigate any potential deficit of people highly trained in these quantitative methods, because I feel that there are two sort of problems that it creates, right? On the one hand, you have a lot of people who are super willing to solve real world problems with big data science, right? And you need to catch them up to speed. But on the other hand, you don't want to make any, incorrect, haphazard inferences.
So the question is, what happens when people get too gung-ho about data science?
Exactly.
Okay.
What do we do to, mitigate that?
Okay.
Well, we definitely see this from an employer side. So we'll sometimes go to recruitment events for data scientists where the recruiters far outnumber the candidates in the room. That's how much demand there is for this skill set right now. And for me, the solution to this is creating pathways for young scientists and people earlier in their careers in general to have exposure to data science practices so that they can learn whether or not it's a good fit for them, something they're interested in, and develop the skill set. So I think there's a couple ways that I think about doing this. One I bet everyone in this room is familiar with is the idea of having open competitions online, like the ones that Renee talked about, which I've seen just be a gateway into data science for so many people, and I think are incredibly valuable. From a more formal perspective, I think part of the thing that sort of academia needs to do is create pathways for students to get experience practicing data science in an applied setting in industry. And of course, in a lot of fields, this is standard practice already. In statistics and engineering, it's very common, especially for graduate students to do internships. But in some other fields, actually in astronomy, in physics, and in other domains, that's very unusual and frankly often frowned upon. And I think that's actually anti-productive for science as an enterprise to develop this skill set and to be able to take advantage of it, and certainly for society at large and for employers to have candidates who are experienced and really skilled and know that they're interested in that topic.
So this is, I think, a really important thing to discuss, I think, because particularly in, say, astronomy, right, which is already open to large data, already has people doing, data science and potentially in another name. But there is this perception that, first of all, if you introduce students to data science in astronomy, they will leave, right? So there's this fear like you don't put your best students to work on anything data sciencey because they will leave.
She meant leave astronomy, not leave data science, just to be clear.
Yeah, sorry, leave astronomy for data science. And sometimes I think colleagues can be scared of that. But then the other bias sometimes that I hear from my more senior colleagues, is that exactly to what you alluded to. Are we teaching them? I mean, someone said to me once, "Are you doing physics or statistics?" And I was like, both. But I think, particularly in my field, we've always really needed to do surveys in cosmology because we have to understand things, on a population level of the universe rather than individual. But some other groups, I think, you could only study your kind of object or your star or your region in the universe. And so there's a paradigm shift that has to happen as people realize that you can do both. You can get the answers that you need astronomically and excite people, as you said, with real-world data science problems. And then if they leave, fantastic, and if they don't, fantastic. But often I find myself having discussions with colleagues about sort of whether or not we should be allowing people to call it science or astronomy if they're doing something that is effectively statistics and data science and computer engineering, which to me is just a moot point. It's just...
I think it's it's a question that hasn't been answered. In social sciences, the expectation is that if you're wanting a PhD in, let's say, political science, you need a master's in CS or computer science or statistics. That's increasingly the norm. Or you're spending many years or 2 or 3 years in your PhD just training on the technical skills, and then you don't have the theory. So it's an issue that is not resolved. Some have proposed, can we work just across disciplines? But that collaboration is very difficult unless both collaborators actually know something about where the other is coming from. So I don't know that we have an existing kind of answer to how exactly we change this in academia in terms of training, given the time constraints.
Yeah.
Yeah, and as the student perspective, I think the internet has made it really easy to try to learn new skills in terms of people putting their code up on GitHub and in a public way, so we can just go through and it's commented and we can see what they did. And I think that the internet has really made it so that we can try to figure it out on our own. We don't necessarily have to take a course on it. I don't at Princeton, I don't think we we don't take courses in our PhD, but there aren't data science for biology courses yet. But I think that informally online we've been able to pick up a lot of that.
David, you have a question? It's right behind you.
So if I could just also make a comment first, which is that we're launching a new Masters of Data Science here within the FAS, and kind of on this note about the supply and demand, we got 1,300 applications and we made 70 offers. So it's there's a huge number of students out there in the world that are looking to do a data science master's, and clearly programs like Harvard are not going to be able to supply all of that. So we do need to really think carefully about this. And this is a very integrated program. My question was, a lot of us are seeing this revolution happening right now with the black box kind of end-to-end models. A number of you mentioned convolutional neural nets, but also many of you, and especially Nathan, talked actually about very detailed models that clearly have been crafted extremely carefully by people with high expertise in the domain. And I just wanted to invite you to talk about that. I'm curious about, in your case, how many years of effort have gone into getting your team to the place where you're able to craft those models that can really provide insight, and invite others on the panel to talk to that as well.
Maybe I can give the first response, which is that I think it's incredibly important for those on my team at Legendary to build that domain expertise if we really want to be in a position to create a positive impact for the rest of the company, and particularly to be able to collaborate and really support effectively the creative side of our company. It's our responsibility, it's incumbent on us to build that domain expertise, to be able to, again, to interpret our models, to understand what consequences the comparisons between model and data that we're making have for decision-making in the company, and to be able to communicate back to them in terms that are going to be understandable and actionable, how our inferences should change their decision-making. So it absolutely is a challenge and a process that we've had to go through over a period of about 4 years now to do that. And I think we're still learning every day. And it's a fantastic opportunity for those of us who are at Legendary to be able to interact directly with incredibly skilled, talented, and experienced creative people in our company for us to be able to build that domain expertise. And it's really, it's a pleasure to be able to have that collaboration.
And we have to move on to coffee, but just to clarify for David, is it right that you started that group at Legendary and that 4 years is how long you've been doing this?
So I was one of the first people to join the group. It was
Right.
started by Matt Merolda, who's our chief
Okay.
analytics officer, who came
Okay.
from a sports domain.
Okay,
So
and then, but it was you and him, and now it's how many people
So now we have about 70 people across our applied analytics division.
in 4 years?
Right.
There's your answer, David. Okay, so what I'm going to do now is I'm going to suggest that we thank all the speakers